Google CP Network Connectivity Center versus AWS Transit Gateway. Welcome to the channel. Please consider subscribing. I produce videos daily covering a wide variety of cloud topics with focus on networking. Also, hit the bell icon to get notified of new videos. In this series, we are doing a deep dive comparison of two of the most powerful cloud networking services available today: Google Cloud's Network Connectivity Center and Amazon Web Services Transit Gateway. Both services solve the same fundamental problem: how do you connect multiple networks together at scale in the cloud? But they approach that problem with very different architectural philosophies. AWS Transit Gateway, often abbreviated as TGW, was introduced in 2018 and quickly became the standard hub-and-spoke network aggregation service in AWS. It allows you to connect VPCs, VPN connections, and direct connect gateways through a single managed gateway, eliminating the complexity of creating point-to-point peering connections between every network pair. GCP Network Connectivity Center, or NCC, is Google's answer to the same challenge. Launched in general availability in 2022, NCC takes a more flexible approach by treating connectivity as a graph of spokes attached to a hub, with support for hybrid connectivity including on-premises networks, third-party SD-WAN appliances, and inter-VPC routing, all from a single control plane. Over these slides, we will examine both services from the ground up: their architecture, routing models, feature sets, scalability, pricing, and the use cases where one outperforms the other. Whether you are an architect deciding which cloud to standardize on or an engineer migrating between platforms, this comparison will give you the depth you need. AWS Transit Gateway. Attachment types. Transit Gateway derives its power from the variety of network resources it can connect. Understanding each attachment type is essential because the attachment type determines how routing works, what bandwidth limits apply, and what additional configuration is required. The first and most common attachment type is the VPC attachment. When you attach a VPC to a transit gateway, you select one subnet per availability zone where the attachment endpoint is placed. AWS creates an elastic network interface in that subnet, and all traffic from the VPC to the TGW flows through that ENI. This means your VPC route tables need a route pointing toward the transit gateway for any destination you want to reach through it. VPC attachments support up to 50 gigabits per second of bandwidth per availability zone. The second type is the VPN attachment. This connects an AWS site-to-site VPN to the transit gateway. Each VPN connection provides two IPsec tunnels for redundancy, each supporting up to 1.25 gigabits per second. ECMP, equal cost multipath routing, can be enabled across multiple VPN connections to aggregate bandwidth beyond the single tunnel limit. The third type is the Direct Connect Gateway attachment. This allows a dedicated physical connection from an on-premises data center to reach any VPC attached to the transit gateway in the same region. Direct Connect offers more predictable latency and higher throughput than VPN connections, making it preferred for production hybrid workloads. The fourth type is the Transit Gateway Peering attachment, which connects two transit gateways in the same or different AWS regions. This is what enables global network topologies. Traffic between peered transit gateways travels over the AWS Global Backbone Network, avoiding the public internet entirely. Finally, there is the Connect attachment, which enables third-party SD-WAN and network virtual appliances to integrate with transit gateway using GRE tunnels and BGP for dynamic routing. This is particularly useful when your organization already has an SD-WAN deployment and wants to extend it into AWS without reconfiguring the existing appliances. What is GCP Network Connectivity Center? GCP Network Connectivity Center, commonly referred to as NCC, is Google Cloud's centralized connectivity management service. It was designed with a broader scope than AWS Transit Gateway from the start. While TGW focuses primarily on connecting VPCs and on-premises networks within the AWS ecosystem, NCC was architected to also support site-to-site data transfer between on-premises locations, routing traffic through Google's backbone even between two non-Google networks. The fundamental model in NCC is the hub and spoke topology. A single NCC hub resource is created per project, and all connectivity is expressed as spokes attached to that hub. Each spoke represents a specific network connection endpoint. A VPN tunnel, a cloud interconnect VLAN attachment, a router appliance virtual machine, or a VPC network. The diagram shows the NCC hub and spoke model. The NCC hub sits at the center of the topology. 4 spokes radiate outward from the hub. The first spoke connects to a HAVPN connection, which represents an on-premises site connected via IPsec VPN tunnels. The second spoke connects to a cloud interconnect VLAN attachment, representing a dedicated physical interconnect from a colocation facility. The third spoke connects to a router appliance, which is a virtual machine running third-party SD-WAN or firewall software that participates in routing via BGP. The fourth spoke connects directly to a VPC network, providing internal Google Cloud workload connectivity. A critically important feature that distinguishes NCC from AWS TGW is data transfer between spokes. In NCC, if you enable the data transfer option on the hub, traffic from one spoke can be forwarded through the Google backbone to another spoke, even if both spokes represent on-premises networks. This means you can use Google's global backbone as a private WAN between your own data centers. AWS Transit Gateway does not natively support this use case. It only forwards traffic between AWS managed network endpoints. NCC integrates deeply with Cloud Router, Google's BGP routing service, to exchange dynamic routes between spokes. All route advertisements flow through Cloud Router instances associated with each spoke, giving you a consistent routing model regardless of whether the spoke is a VPN, interconnect, or appliance. GCP NCC, Routing Model and Cloud Router Integration. NCC's routing model is built on top of Cloud Router, Google's managed BGP service, which handles all dynamic route exchange between spokes and the hub. Understanding how Cloud Router integrates with NCC is essential for understanding how routes propagate throughout your network topology. Every spoke that uses dynamic routing, HAVPN, Cloud Interconnect, and Router Appliance spokes, requires a Cloud Router instance in the same region as the spoke. The Cloud Router establishes BGP sessions with the remote peer, whether that is an on-premises router, a VPN concentrator, or an SD-WAN appliance. Routes learned over those BGP sessions are then exported to the NCC hub and redistributed to other spokes that are configured to receive them. The diagram shows the route propagation flow within NCC. Cloud Router sits between each spoke and the NCC hub. When an on-premises router connected via HAVPN advertises its network prefixes over BGP, those prefixes travel to the Cloud Router associated with the VPN spoke. The Cloud Router then exports those prefixes to the NCC hub. The hub redistributes them to all other spokes whose import policies accept those routes. A Cloud Router associated with a router appliance spoke receives those redistributed routes and further advertises them to the SD-WAN appliance over another BGP session. The same redistribution happens in reverse when the SD-WAN appliance advertises branch network routes. NCC supports 2 routing modes for VPC spokes. Regional routing, where only routes in the same region as the spoke are exchanged, and global routing, where routes from all regions in the VPC are exchanged with the hub. Global routing mode is required when you want workloads in multiple Google CP regions to be reachable from on-premises through a single NCC configuration. Unlike AWS TGW route tables, NCC does not currently expose multiple isolated route domains at the hub level. Route filtering is implemented at the cloud router level using custom route advertisements and BGP community filtering, which requires more deliberate configuration to achieve the same isolation patterns that TGW achieves through multiple route tables. Scalability and limits comparison. Understanding the scalability limits of both services is critical when designing large-scale enterprise networks. Both Transit Gateway and NCC impose hard limits on the number of attachments, routes, and bandwidth they support, and those limits can become architectural constraints in large deployments. For AWS Transit Gateway, the key limits are as follows. A single TGW supports up to 5,000 attachments, which includes all VPC attachments, VPN connections, direct connect gateways, and peering attachments combined. Each TGW route table can hold up to 10,000 routes. A VPC attachment supports up to 50 gigabits per second of bandwidth per availability zone. VPN attachments are limited to 1.25 gigabits per second per tunnel, with ECMP allowing aggregation across multiple tunnels. TGW Connect attachments support up to 5 gigabits per second per attachment, with up to 4 Connect peers per attachment enabling 20 gigabits per second of aggregate throughput. Bandwidth across a TGW peering connection between regions is limited to 50 gigabits per second. For Google CP Network Connectivity Center, the key limits are as follows. An NCC hub supports up to 250 spokes per hub. Each HAVPN spoke contributes up to 4 tunnels, each at 3 gigabits per second, for up to 12 gigabits per second per spoke with ECMP. Cloud interconnect spokes can operate at 10 gigabits per second or 100 gigabits per second depending on the circuit type. Router appliance spokes support up to 2 BGP peers per appliance virtual machine, and you can deploy multiple appliance virtual machines per spoke for redundancy and scale. NCC supports up to 15,000 dynamically learned routes per hub across all spokes, with a limit of 200 static routes per hub. The diagram compares the scalability limits of both services side by side. You can see that AWS TGW has a significantly higher attachment limit, 5,000 versus NCC's 250 spokes, making TGW more suitable for environments with a very large number of small VPCs, such as multi-tenant software as a service architectures where each customer receives an isolated VPC. NCC's lower spoke limit is partially offset by its global hub model, which removes the need to create separate regional hubs and peer them together, as is required in TGW for multi-region deployments. In terms of route table scale, TGW's 10,000 routes per route table gives it an advantage in environments with many small networks, while NCC's 15,000 routes per hub provides sufficient capacity for most enterprise topologies. For bandwidth-intensive workloads, NCC's support for 100 gigabits per second interconnect spokes gives it a clear advantage at the high end. Pricing model comparison. Pricing is often the deciding factor in cloud architecture decisions, and both Transit Gateway and NCC use consumption-based pricing models that can produce significantly different bills depending on your traffic patterns and topology. Let us break down exactly how each service charges. AWS Transit Gateway pricing has 3 components. First, there is an attachment fee charged per hour for every resource attached to the gateway. As of current pricing, a VPC attachment costs approximately $0.05 per hour, which works out to about $36 per month per VPC. A Transit Gateway peering attachment costs the same per hour. Second, there is a data processing fee of $0.02 per gigabyte for all data that passes through the gateway, inbound and outbound combined. Third, for Transit Gateway Connect attachments, there is an additional $0.05 per hour per attachment on top of the data processing fee. For a deployment with 50 VPCs, the attachment cost alone reaches $1,800 per month before any data transfer is counted. In a high-throughput environment processing 100 terabytes per month, the data processing fee adds another $2,000. These costs can accumulate quickly in large-scale deployments, and engineers often discover TGW costs are significantly higher than expected when they account for all data flowing between VPCs, including monitoring agents, backup traffic, and service mesh telemetry. Google CP Network Connectivity Center pricing also has multiple components. There is no per spoke hour attachment fee for VPN or interconnect spokes. You pay for the underlying VPN or interconnect resource, not for the NCC attachment itself. VPC network spokes do incur a per hour charge. Data transfer through NCC between spokes incurs a per gigabyte charge that varies by region and spoke type. Site-to-site data transfer, where NCC routes traffic between two non-Google CP spokes, has a higher per gigabyte rate since it uses Google's backbone as a transit medium. The key insight in this pricing comparison is that TGW charges for both attachment time and data volume, while NCC primarily charges for data volume and the underlying connectivity services. For environments with many VPCs but modest traffic between them, NCC may be cheaper per month. For environments with few VPCs but very high throughput, TGW's flat attachment fee may become the dominant cost while NCC's data processing fees dominate. Always model your specific traffic patterns before committing to either service at scale. High availability and redundancy patterns. High availability is not an afterthought in cloud networking, it is a foundational design requirement. Both AWS Transit Gateway and GCP Network Connectivity Center are built on redundant infrastructure internally, but the way you design redundancy around them differs significantly, and getting it wrong can leave your network with a single point of failure that the managed service itself cannot protect against. Starting with AWS Transit Gateway, the service is itself a regional resource that AWS operates with high availability across multiple availability zones within the region. However, the attachments you create to connect VPCs are your responsibility to make resilient. For VPC attachments, best practice is to specify subnets in at least 2 availability zones when creating the attachment. This places TGW elastic network interfaces in multiple AZs, ensuring that if one AZ experiences a failure, traffic can still flow through the ENI in the surviving AZ. For VPN attachments, each site-to-site VPN connection already provides 2 IPsec tunnels terminating on different AWS endpoints. However, if you rely on a single VPN connection, a failure of your customer gateway device eliminates your entire on-premises connectivity. Best practice is to deploy 2 customer gateway devices at each on-premises site and create 2 separate VPN connections to the same TGW, with eCMP enabled so both are active simultaneously. For Google CP NCC, HAVPN is specifically designed to eliminate single points of failure. When you deploy an HAVPN gateway, Google CP creates 2 VPN gateway interfaces, each with its own external IP address hosted on independent infrastructure. 4 tunnels connect to 2 remote peer interfaces, providing full redundancy at both the Google side and the on-premises side. This achieves Google's 99.99% availability SLA for the VPN path. The diagram shows both redundancy models side by side. For Transit Gateway, you see 2 customer gateway devices each with their own VPN connection creating 4 tunnels total to the same transit gateway. For Network Connectivity Center, the HAVPN gateway is shown with its 2 internal interfaces, each connecting to the on-premises peer through 2 tunnels, forming a full mesh of 4 tunnels. Both approaches achieve active-active redundancy using equal-cost multipath to utilize all tunnels simultaneously under normal conditions. Dedicated circuits. Direct connect versus cloud interconnect. For production hybrid workloads demanding predictable latency, higher throughput, and traffic that avoids the public internet entirely, both AWS and GCP offer dedicated physical circuit options. AWS provides Direct Connect, and GCP provides Cloud Interconnect. Both services integrate with their respective network hubs, Direct Connect connects through a Direct Connect gateway to a transit gateway, and Cloud Interconnect VLAN attachments connect directly as NCC spokes. Let us examine the architecture and capabilities of each. AWS Direct Connect establishes a dedicated network connection from your on-premises data center or colocation facility to an AWS Direct Connect location. Circuit speeds are available at 1 gigabits per second, 10 gigabits per second, and 100 gigabits per second. A single physical Direct Connect connection can carry multiple virtual interfaces, or VIFs, each of which connects to a different AWS service. A private VIF connects to a specific VPC. A transit VIF connects to a Direct Connect gateway which then routes to one or more transit gateways, and a public VIF provides access to AWS public service endpoints. For integration with TGW, you create a transit VIF connected to a Direct Connect gateway, and associate that Direct Connect gateway with your transit gateways in up to 3 regions. This allows a single Direct Connect connection to serve VPCs in multiple regions through a single attachment chain. For redundancy, AWS strongly recommends provisioning 2 Direct Connect connections from different physical facilities or from the same facility through different devices. A single Direct Connect connection without redundancy does not qualify for an SLA, while a redundant configuration with 2 connections from separate locations achieves 99.99% availability. The connections should terminate on different Direct Connect routers and associate with the same Direct Connect gateway so failover is automatic via BGP route withdrawal. Google CP Cloud Interconnect is available in 2 forms. Dedicated Interconnect provides a direct physical connection between your network and Google's at a Google colocation facility, available at 10 gigabits per second or 100 gigabits per second per circuit. Partner Interconnect uses a service provider to establish connectivity where Dedicated Interconnect is not available, at speeds from 50 megabits per second to 50 gigabits per second. For NCC integration, each physical circuit is subdivided into VLAN attachments, each of which becomes a separate NCC spoke. A single 100 gigabits per second Dedicated Interconnect circuit can carry dozens of VLAN attachments, each serving a different VPC or purpose, without requiring additional physical infrastructure. Google CP requires 2 VLAN attachments in different metropolitan areas to achieve the 99.99% SLA for Cloud Interconnect, following the same principle of geographic diversity that AWS applies to Direct Connect redundancy. Google's colocation facilities are present in all major metro areas worldwide, providing broad geographic availability for Dedicated Interconnect. SD-WAN Integration Architecture. Software-defined WAN integration is one of the most strategically important capabilities for enterprise networks, because most large organizations already have an SD-WAN deployment connecting their branch offices and data centers. The ability to extend that SD-WAN into the cloud without rebuilding the entire architecture from scratch is a significant operational advantage. Both AWS TGW and GCP NCC support SD-WAN integration, but the mechanisms are architecturally different and favor different vendor ecosystems. AWS Transit Gateway supports SD-WAN integration through the Connect attachment type. A Connect attachment uses a Transit Gateway Connect peer, which establishes a GRE tunnel between an EC2 instance running the SD-WAN appliance and the TGW. BGP sessions run inside the GRE tunnel to exchange routes dynamically. Each Connect peer supports up to 5 gigabits per second of bandwidth, and you can create up to 4 Connect peers per Connect attachment, giving up to 20 gigabits per second of aggregate throughput per appliance. The EC2 appliance instance bridges traffic between the GRE tunnel on the TGW side and the SD-WAN overlay fabric that connects your branch offices. Google CP National Connectivity Center's router appliance model was designed specifically for SD-WAN integration from inception. A router appliance is a compute engine virtual machine running a third-party network virtual appliance NEBGP-capable software that Google CP has certified through its National Connectivity Center Router Appliance Partner Program. Cloud Router establishes a BGP session directly with the appliance virtual machine's internal IP address, eliminating the need for GRE tunnels. The appliance advertises branch network prefixes to Cloud Router, which passes them to the National Connectivity Center hub for redistribution to other spokes. Return routes are received by the appliance from Cloud Router and programmed into the SD-WAN overlay for forwarding to the appropriate branch. The diagram shows the complete SD-WAN integration flow for NCC. The SD-WAN controller manages the SD-WAN overlay across branch offices and the cloud appliance. The router appliance virtual machine in GCP participates in BGP with Cloud Router on the left side, and in the SD-WAN overlay protocol with remote branches on the right side. Branch prefixes enter the NCC hub through the router appliance spoke, are redistributed by the hub to the VPC spoke and the HAVPN spoke, and reach cloud workloads and other connected sites. Traffic from cloud workloads destined for branch offices follows the reverse path through the router appliance. Key certified SD-WAN vendors for NCC router appliance include VMware SD-WAN by Broadcom, Cisco Catalyst SD-WAN, Palo Alto Prisma SD-WAN, Juniper Session Smart Router, and Aruba Edge Connect. AWS TGW Connect is supported by similar vendors but requires appliance images available in AWS Marketplace and the GRE tunnel configuration that NCC eliminates. Monitoring, logging, and observability. Operational visibility into your network hub is essential for troubleshooting connectivity issues, investigating security incidents, and capacity planning. Both AWS Transit Gateway and GCP NCC integrate with their respective cloud monitoring platforms, but the depth and granularity of observability data differs between the two services, and knowing what telemetry is available informs how you design your operations tooling. AWS Transit Gateway publishes metrics to Amazon CloudWatch. The core metrics available are bytes in and bytes out, which measure traffic volume entering and leaving the TGW per attachment. Packets in and packets out, which count packets rather than bytes. Packet drop count black hole, which tracks packets dropped due to black hole route matches. And packet drop count no route, which tracks packets dropped because no matching route exists in the route table. These metrics are published per Transit Gateway and can be broken down by attachment, allowing you to identify which VPCs or VPN connections are generating the most traffic or experiencing the most drops. CloudWatch alarms can be set on any metric to notify operations teams when thresholds are breached. For flow-level visibility, AWS VPC flow logs capture network traffic at the VPC level, including traffic traversing TGW attachments. You can enable flow logs on the VPC or on individual ENIs, including the TGW attachment ENIs, to capture source IP, destination IP, protocol, port, packet count, byte count, and whether the traffic was accepted or rejected. Flow logs are delivered to CloudWatch Logs, Amazon S3, or Amazon Kinesis Data Firehose for analysis. GCP NCC integrates with cloud monitoring for metrics and cloud logging for flow logs. VPC flow logs in GCP capture similar fields to AWS flow logs, including the source and destination virtual machine names and regions in addition to IP addresses, which makes correlating traffic to specific workloads easier than in AWS where you must cross-reference IP addresses with instance metadata separately. Cloud Router logs capture BGP session state changes, route advertisements, and route withdrawals, providing detailed visibility into the dynamic routing behavior of all NCC spokes. These logs are invaluable for troubleshooting situations where routes are not being propagated correctly between spokes. The diagram shows the observability pipeline for both platforms. CloudWatch receives TGW metrics and VPC flow logs for AWS. while cloud monitoring receives NCC spoke metrics and cloud router BGP logs for GCP. Both feed into their respective logging and analysis services. CloudWatch logs and insights for AWS, and cloud logging with log analytics for GCP. Both platforms support export to third-party SIM and observability tools for organizations that use centralized tooling across multiple cloud providers. Migration considerations. For organizations that are migrating between cloud platforms or consolidating a mixed cloud network architecture, understanding the migration path to or from each hub service is essential. Network migrations are among the highest risk infrastructure changes because a misconfiguration can disconnect production workloads from each other or from on-premises systems. Let us examine the key considerations for migrating to or between these services. Migrating from VPC peering to AWS Transit Gateway is the most common TGW migration pattern. In a VPC peering architecture, each VPC has direct peering connections to its neighbors. The migration requires adding TGW attachments to all VPCs, updating VPC route tables to point to the TGW instead of the peering connection for each destination, and verifying connectivity through the TGW before removing the peering connections. Because VPC peering and TGW attachments can coexist simultaneously, this migration can be done gradually, moving one VPC pair at a time to TGW routing while leaving others on peering, allowing rollback at each step. The risk is managed by maintaining both paths until validation is complete. Migrating from GCP VPC peering to NCC VPC spokes follows a similar pattern. GCP VPC network peering is also non-transitive, and the same scaling limitations apply. Attaching VPCs to NCC as spokes while maintaining existing peering connections allows a gradual migration. The key difference in GCP is that NCC requires cloud router for dynamic routing even for VPC spokes, so organizations that have relied on static routes must adopt BGP as part of the migration, which can be a significant skills investment for teams unfamiliar with BGP. For organizations migrating workloads from AWS to GCP or vice versa, the network migration must be coordinated with the workload migration. A common approach is to establish cross-cloud connectivity first using a dedicated interconnect or VPN between AWS TGW and GCP NCC so that migrating workloads can communicate with the systems they depend on in the source cloud during the transition period. AWS TGW and GCP NCC can be connected to each other through standard IPsec VPN or through a co-location cross-connect, with BGP exchanging routes between the two hubs. The diagram shows a hybrid migration architecture where AWS TGW and GCP NCC are connected via an IPsec VPN. Routes from AWS VPCs are advertised through the TGW VPN attachment to the NCCHA VPN spoke, and vice versa. During the migration, workloads in both clouds can communicate, and as each workload moves from AWS to GCP, its routing simply shifts from the TGW originated prefix to the NCC VPC spoke prefix. This allows zero downtime migration of individual services while maintaining end-to-end connectivity throughout the process. Summary and final recommendations. We have now covered the full landscape of the AWS Transit Gateway versus GCP Network Connectivity Center comparison, from foundational architecture through attachment types, routing models, redundancy patterns, dedicated circuits, security segmentation, SD-WAN integration, multi-region design, observability, and migration strategy. Let us consolidate the most important takeaways into a final summary. AWS Transit Gateway is the right choice for AWS-centric organizations with many VPCs requiring clear network segmentation through route tables, teams that prefer static and policy-based routing over BGP-heavy configurations, and deployments where the 5,000 attachment limit matters because VPC count is very high. Its data processing fee model rewards environments with many VPCs but moderate traffic volumes, and its regional architecture gives explicit data sovereignty control per region. Google CP Network Connectivity Center is the right choice for organizations needing to use Google's backbone as a private WAN between on-premises sites, teams deploying certified SD-WAN appliances who want native BGP integration without GRE tunnels, and multi-region global deployments where a single hub simplifies operations significantly. Its per-spoke architecture with global reach rewards environments prioritizing bandwidth and international connectivity over sheer VPC count. The router appliance ecosystem is broader and more deeply integrated than TGW Connect for SD-WAN use cases. For organizations operating in both clouds, treat each service as the hub for its respective cloud ecosystem and build cross-cloud connectivity through VPN or dedicated interconnect between the two hubs. Neither service is universally superior. The right choice is always the one that best fits your existing environment, team skills, traffic patterns, and long-term cloud strategy. Thank you for your attendance. Please consider subscribing to the channel and liking this video.